Archiving started.
Good morning and welcome to the lecture on Chapter 8, Sampling Distributions and Hypothesis Testing. Here I provide an example from you. This is actual published research on the prevalence of smoking for Americans older than or equal to 18 years of age. We can ask a number of questions about the data you see above. Just from looking at the graph and thinking about the things we talked about earlier in the series where we discussed bar graphs. What do you notice about the particular trends in this bar graph? I'll give you a minute to kind of take a look. So we know when we're reading data, especially in a graphical format, it's important to look at your X and Y axes, of course, to see what exactly we're measuring here. So what's on your y-axis will sort of get at that outcome variable. We see that's the percent of population. We know we're looking at prevalence of smoking, so we can look at those across various ethnic groups. So you can see the different bar graphs represent those different races or ethnicities. You can quickly see the light purple bars. For those of you who may be colorblind, the one all the way to the right. For men, it appears that American Indian men have the highest prevalence rate for smoking, and the same for women. American Indian women have the highest prevalence rate for smoking. And you can see at the bottom here, we see that's from a National Health Interview Survey, and that total N, yes, that's correct. That's the sample size, and you can see that we had a huge sample size in this study of over 30,000 individuals. We may want to, as researchers, ask particular questions about smoking, race, ethnicity, and gender. So we come up with a research question. So for example, we could ask what groups might differ in their rate of smoking from what other groups. Okay, so we can compare particular groups, and that's largely driven by theory. So as researchers, there's particular background research that we would conduct in order to come up with a particular research question followed by a hypothesis. So perhaps we're interested in gender differences in prevalence rates of smoking. So then we would just compare on the previous slide males versus females. Or perhaps it's more interesting to take a look at non-Hispanic white individuals versus the other groups. So as you can see, there's a number of various research questions we could ask. And based on the prior data that was shown, there are differences in all of those cases, the ones that I've listed above. But what we want to know is more so, could they just be due to chance? We can just see, just from looking at the demographics or the summary statistics here, that there does appear to be a difference between men and women. The rates are different. Or let's say if we were just looking at American Indian men, where the rates are 37% of the population smoke, versus women, where we have 33%. So there's a difference there. 37 obviously is different than 33%. But again, we're not sure if that's just due to chance. That's where inferential statistics come into play. We can look at specific targeted research questions and test them using statistical analyses to determine whether those changes or those differences occurred due to truly differences in the population rather than just occurring by chance. So here's a couple of questions that we can look at. Okay, what's the probability of one having coronary heart disease given that they're a smoker? And based on the literature, we know that people who are smokers, their probability of having coronary heart disease is 2 to 4 times more likely than those who are non-smokers. That's based on inferential statistics. Those numbers are generated from data, and they give us the ability to state with confidence at a particular degree or level that this occurrence is true in the population and did not occur by chance. Similarly, we can say, what is the relationship between cigarette smoking and stroke? Written in probability terms based off of the previous lecture, we use conditional probabilities here. So remember that vertical bar that we use. What is the probability of one having a stroke given that they are a smoker. And it's approximately 2 times more likely than the probability of those who have a stroke who are non-smokers. So we can see that there's an increased risk of stroke and coronary heart disease with being a smoker. And that's based on inferential statistics. You may remember the term inferential statistics from one of our earliest lectures in this course. You might recall, and the slide's actually taken from that statistics is a way of thinking that recognizes the role of variability. And we've talked about variability now in an earlier lecture. So that's our standard deviation, the dispersion of our scores in a particular data set. It also recognizes the role of chance and error. And statistics applies that way of thinking to understand the results of research and events in everyday life. So statistical inference is the ability to decide whether the differences that we see in our data set are big enough, meaning that they're likely to have not occurred by chance. Let's think about gender and PY214 enrollment as an example. Okay, so if I were to poll and ask how many men and women are in the class, okay, we could then get some summary data where we could see perhaps there are 70 males and 100 females in the course. Okay, so just by polling you and asking you that simple question, I've now collected some data about the course and some characteristics about the actual sample. My sample being this online PY214 class. A research question may be, is the difference in numbers of men and women in this class too large to have likely occurred by chance? So in other words, was it just by chance that more females signed up for the course this semester? Or is it instead the fact that more women take online courses in statistics? Okay, so you understand the difference between those two? So we're trying to determine whether the difference between men and women in this class is too large to have likely occurred by chance. So we need to think about what population do students in this class actually represent. Yeah, I'll give you a minute to think about that. I used the word sample when I talked about the fact that I sampled from this particular PY214 online course. But our research results, they may generalize to a larger population. Remember the difference between a sample and a population here. So what is the population? What population do you guys represent? One might argue that you represent all undergraduates taking a statistics course in a public university. Okay, so that's one option. On the other hand, you may be part of a population of students taking online courses, or more specifically, students taking online statistics courses. Okay, so it's important to define your population. When we said likely above, so is the difference in this class too large to have likely occurred by chance? How sure do we want to be? Okay, so with what confidence level are you wanting to proceed? Do you want to be 95% confident that the chance, or that the difference is too large to have occurred by chance? What about 99%? Okay, so we can adjust the confidence levels, and we'll do so in the upcoming series of lectures, so I can show you that you as a researcher actually have control over that. Okay, so you can be more conservative or a little bit more liberal. Generally, though, in psychology and in most sciences, a 95% confidence level is generally accepted. Some people use a more stringent or level of confidence, and that's at 99%. We'll talk about all those things coming up. Also, a third consideration, how many more classes or students drawn from the same population would we need to feel confident in our conclusion? Okay, so I've looked at just this one particular PY214 online class here at UAB. Is that enough? Do you believe that you guys represent the population at hand? There's some things to consider there. So we may think about sample size. In our class, we have, for this semester, fewer than 100 students, let's say. Okay, so how does that compare to other online statistics courses where perhaps there are thousands of students? Okay, so it might be important to actually sample from multiple online PY214 classes. So with a larger sample size, we may be more confident more confident in that the difference truly does exist and it's not likely to have occurred by chance. Okay, you may recall from one of our early lectures where I gave an example about a diet. Okay, you remember that? So some people received a diet drug and others did not. Here we can ask the research question, are the differences between the experimental and control groups too likely to have occurred by chance? Too large to have likely occurred by chance. And again, we're saying that's assuming that there's no difference in the population. When we want to answer questions like that, we need to know about sampling distributions. So this is a new term that I want you guys to be familiar with, and hopefully you've read in the chapter about sampling distributions. Simply, the distribution of a statistic over repeated samples from a specified population. So for example, if we wanted to look at the distribution of the probability of one being a smoker, we may take repeated samples of men and women of each gender and ethnicity. Okay, and so that's similar to what that National Health Survey did. So they had 31,000 participants in their study, so they took repeated samples of men and women. Okay, so that means from various sources, from various genders, from various ethnicities, in order to be balanced on that. We can also take repeated samples of undergraduates in the previous example that I explained, if we're interested in looking at the distribution of one being a male or one being a female. So I gave the example, we can look at one sample, that's this course, but what about all of the other online statistics courses? Okay, so we can take repeated samples of various online courses, all of those taking the distribution of a particular statistic, looking at gender in that case, over repeated samples, and all of you come from a specified population. So we would set those parameters. For example, if I were to poll students from online statistics courses, then that would be the specified sample, and so I would repeat and take those. Let's say in the population, in the United States, let's say there happens to be 10,000 undergraduate online statistics courses being taught. Okay, so that's the population. Remember, because of time constraints, financial constraints, and just an almost impossible ability to get in and actually recruit all of those or sample from all of those classrooms, we would just take a particular sample of those. A sampling distribution would be to take, let's say, 50 of the 10,000 courses and to poll from each of those 50 classes and find out how many are men and how many are women that are taking those. Does that make sense? We can also look at other questions, and here, the distribution of weight loss over repeated samples of participants in two groups. Let's say we had an experimental group who took a particular diet drug versus a control group who received a placebo. Okay, so that's where inferential statistics come in, and this is where we have a sampling distribution which helps us be able to better characterize the population at hand. Here's an actual example from the literature. So this is a study conducted by Bushman in 1998 who was asking the potential research question, does violent content in a video affect later behavior? So what Bushman did was brought in two groups of 100 subjects who saw a video. He randomized those subjects into two groups. Half of the participants watched a violent video, and the other half watched what was deemed a non-violent video. And then they were to free associate words, okay, which had both an aggressive and a non-aggressive meaning. So, for example, the word cuff, mug, I've given some examples down there. Here are the results. So those who actually saw the violent video, they had more aggressive free associates. Okay, you can see there the mean level was about 7 free associates for those who saw that violent video. And then for those who saw the nonviolent video, they had on average 5.5 aggressive free associates. So just from looking at these summary statistics or this descriptive data, you can see that apparently there is some difference here, right? There is a difference between 7.10 and 5.65. So that's descriptive statistics. Looking at just the mean, we can say that those who saw a violent video appeared to report more aggressive free associates than those who saw the nonviolent video. What still remains a question, however, is whether this difference between 7 and 5.5 is large enough to conclude that this type of video actually affected the results. Or perhaps it was just due to chance. So that's where the inferential statistics come in. Okay, we talked about 2 groups. I'm going to simplify that study into 1 group in order to sort of illustrate this point to you. Okay? So we're going to convert it into a one-group study. So we know that people normally give about 5.5 aggressive associates to hominins. All right, so that's our population parameter. When we say people normally, what we mean is that that's indicative of our larger population here. Okay? Then we brought in a group who watched violent videos, and they gave 7.10 aggressive associates. That's a sample statistic, not a population parameter. Here we're talking about our individual data set, okay, and the results that we receive from our individual sample. Now we want to see, is this sufficiently more than expected to conclude that the video had an effect? So what's the true question here? What's the statistical question? That is the difference between 7.10 and 5.65 large enough to lead us to conclude that it is a real difference, that it is not likely to have occurred by chance? Another way to ask this is, would we expect a similar kind of difference with a repeat of this experiment? Or is the difference due to sampling error? Sampling error, new term that I want you guys to know. Remember, statistics account for variability and they account for error in our data. So the normal variability that we would expect to find from one sample to another, that's our sampling error. Random variability among observations or statistics, that is just due to chance. How can we actually assess sampling error? Well, we can take many groups of 100 subjects. That's one way, right? We can record the aggressive responses of those groups, and we can plot that distribution, and we can record its mean and standard deviation. That's what's known as a sampling distribution. Remember, we're taking or looking at a statistic over repeated samples of a population, of some specified population. And here's what a sampling distribution might actually look like. Do you remember what type of graph this is from our displaying data chapter? Okay, so what we have here is a histogram. And you can see that we're looking at, on the x-axis this time, the mean number of aggressive associates, and the frequency is now plotted on our y-axis. And you can see that that sampling distribution, it's unimodal. It looks pretty much like a bell curve, so we don't have any particular skew here. Notice in the right, you see that our sample size is 10,000. We also have some sample statistics here. We have a standard deviation and the mean. So that sampling distribution looks quite like a normal distribution. Okay. So what the sampling distribution has shown us is the kind of means we would expect to find when people don't view a violent video. And when people don't view the violent video, they average between 4.5 and 6.5 aggressive interpretations. Now, this is without our experimental manipulation involved. When we actually introduce the experimental manipulation showing the violent video, we find that the group averaged about 7. Okay, so what we conclude here, or what we begin to sort of assume, is that our subjects' responses were not like normal. Normal being the sampling distribution I showed on the previous slide. So this is normal aggressive associates, not having watched the video. You see that the mean there on the right again is around 5.5. Okay, so what we could conclude then, just based on the sample statistics and being able to sort of look at this summary statistics, we conclude that the video appeared to have increased the aggressive associates. Here's a few things about the sampling distribution that I want you to know about. So the sampling distribution is based on, obviously, repeated samples, right, that are based on a specified population. We can get or extract particular bits of information from our sampling distribution. I've already sort of talked about some of these, but you can get a mean and a standard deviation. Okay? If we have an infinite number of samples, then the mean of the sampling distribution is our population mean. So in other words, as the number of samples increases, okay, the more the sampling distribution begins to look like the population mean. And another name for that standard deviation of our sampling distribution is standard error. Okay. A more formal term, a more technical term for what we just did is hypothesis testing. Most of you have been exposed to hypothesis testing, likely in your high school classes and perhaps already in your undergraduate classes here at UAB. You might recall that hypothesis testing is very much stepwise. Okay? So there's particular protocols that we will follow, and we will use those pretty much for the remainder of this course. I hope that most of you will appreciate the consistency that I will use across the next series of lectures because it will help make things a lot easier for you. So we'll use hypothesis testing in order to use our t-tests and our ANOVAs and really any of the statistical tests that we have coming for the remainder of this course. But once you learn the basic outline, the basic steps in hypothesis testing, you can apply those to any type of statistical test that we will use. Okay? One thing you'll need to know with regard to hypothesis testing is that we need to be able to state our null hypothesis. If you think about the word null, okay, that would indicate no change, correct? So that's what we're talking about here. This is the hypothesis that we usually want to reject. Okay, so we're running an experiment. We've initiated or implemented some sort of experimental manipulation. We're hoping that that changes behavior in some way. And that was the purpose of actually conducting the research study, was it not? Was to change or evoke some behavior, to test whether there is a difference when we implement that experimental manipulation. The null hypothesis, on the other hand, is simply stating that there is no difference between groups or between a particular manipulation and another. Okay, so in this particular example, the one we've been using today, the hypothesis that watching that violent video does not change the mean number of aggressive interpretations as compared to those who did not watch a nonviolent video, or excuse me, that watched a nonviolent video. Okay, that's a null hypothesis. No change, no difference between the groups. Okay, so here are the steps in hypothesis testing, and here we talk about them in a generic form. As I mentioned, we'll go over these for the rest of the semester, and we'll become more specific, and it'll become clear to you how we are actually following these same steps over and over again using different statistical analyses depending on our research question and the type of data that we're dealing with. The first step is always to define the null hypothesis. And again, that means no change, that nothing has occurred or no effect. Okay, so then you decide what you would expect to find if the null hypothesis were true. Then we actually look at what we found. We look at the data. We look at the numbers, and then we make some determination based on the data. We either reject the null, okay, if what we found is not what we expected, or we fail to reject the null if what we found is what we expected. Okay, so when we talk about hypothesis testing and the null hypothesis, we're testing the null hypothesis here. Okay, so for example, there's no difference between a population parameter and a hypothesized value. Okay, so you might think about our last example here, the population parameter of 5.65. Was there any difference between that number of aggressive associates and the hypothesized value? Okay, the change in violent videos, the 7.10. Or we can say no difference between a parameter in one population and the same parameter in another population. So the mean for those who watched the video versus the mean of those who did not watch the video. Okay, so there's a number of different ways we can test the null hypothesis. What I want you to understand is that when we are going through hypothesis testing, it is the null hypothesis that we are putting under a test. We want to see whether sufficient evidence is available in our data to reject the null hypothesis. Okay, the logic of our hypothesis testing then comes from theory. We determine some research hypothesis in the beginning. So that's, as researchers, you read literature and you see what others are finding in the particular area. Okay, so as a distracted driving researcher, if I'm going to test the difference between text messaging and talking on a cell phone on driving performance, I need to have some theory. I need to base that on observation. I need to base it on previous studies that have already been conducted. What did others find? That's how I actually develop a research hypothesis. So perhaps others found that there is a significant difference in texting versus talking on a cell phone. Then I might also hypothesize that would occur. That's a research hypothesis. That's a little different than a statistical hypothesis. A statistical hypothesis is talking about within your actual data set what has occurred, whether a change or not a change has occurred. Okay? Then you'd actually set up a mutually exclusive. Do you remember what that term means? If not, you need to go back to the probability lecture and refresh yourself on that. And exhaustive, that's another term we learned last time. We need to set up a mutually exclusive and exhaustive null hypothesis. So in other words, there's no difference between the means. And you can see there I have the capital H and then a sub-zero. Okay? That's how we notate a null hypothesis in this course. Then what we do is we go out and we obtain a representative sample. Do you remember the lecture? I guess it was one of the first ones where we talked about a representative sample. What does that actually mean? And so it must generalize to an actual population based on specific parameters. Okay, and that representative sample that we've obtained, we use that to actually crunch some numbers, compute and obtain a sample statistic. Okay? And then what we do is we determine whether the sampling distribution of that statistic, we determine the sampling distribution of that statistic, okay, that we'd expect if the null hypothesis were true. So we have something to actually compare it to. So that's the next step, comparing. We compare that obtained value of the sample statistic. In other words, from 3A on the previous slide, that's based on our data set. That's based on our actual numbers from the data that we've collected. We compare that number to the sampling distribution of the mean. Okay, so that may be our T statistic or our F ratio. Those terms may be a little foreign to you. That's what we're going to be learning about in this course. And then we're going to compute the probability of the obtained value given a particular sampling distribution. And if that obtained value would be highly unlikely, then we reject the null hypothesis. And on the other hand, if the obtained value would not be unlikely, then we do not reject the null hypothesis. So again, in the end, we're making some determination about whether a change occurred or whether no change occurred. And remember that change being not likely due to chance. And why do we actually test the null hypothesis? Okay, remember the definition of statistics. Testing the null hypothesis is a way of acknowledging that the observations of differences in relationships in samples may represent only chance variability. Okay. The second reason is it puts the burden of proof on the data. Okay, so we can demonstrate that the null hypothesis is actually unlikely. So we have the data and we know the shape of our sampling distribution, and if we're confident in our data and they're inconsistent with that null hypothesis, then we simply just reject the null hypothesis. So we've talked about the null hypothesis quite a bit. We also have what's known as the alternative. That's the one that we're saying a change has indeed occurred. Okay. See here with the H sub R, that's how we'll notate a research hypothesis. So our research question may be, the rate of smoking is greater in men than in women. Okay, that's our research question is looking at gender differences in prevalence rates of smoking. The research hypothesis then indicates what we expect to occur. Here we're saying that it's going to be greater in men than women. How do we pick that? We don't just pull it out of the clear blue sky, but based on what I've told you earlier, you actually read literature and you base it on previous studies, empirical evidence, observations. You know, as scientists, we come in with some indication or some idea of what we would expect to occur. We're not always right, and we run the research studies to support our research hypotheses. We then set up the corresponding null hypothesis. That's H sub 0. That's a statistical hypothesis. That's not based on our research. Okay? So it's not your research hypothesis. Instead, we're going to say that the smoking rate is not greater in men than in women. Remember, that's the null. No change. No difference between the groups. The research hypothesis and the null hypothesis are mutually exclusive and exhaustive alternatives. So in statistics, the anti-null, the opposite of the null hypothesis, is called the alternative hypothesis. And we'll use H sub 1 or H sub A to indicate the alternative hypothesis. Just a couple more reminders about sample statistics and test statistics. Okay, you might recall our sample statistics are calculated from a single sample, and they're used to describe a sample. And we use means and mean differences to do this. A test statistic, on the other hand, is derived from those descriptive statistics and has a known distribution, and we use those in our statistical test. So I've talked about some of these already. Z, a T, an F, a chi-square. You may have read some literature, read some studies that use these types of statistical techniques. You're going to know how to do all of those by the end of this course. Okay, so I think we actually were going to stop right there. You might notice in your syllabus that we're going over the first part of Chapter 8 today. We have a second part of Chapter 8 that will come up next week where I'll go over the remainder of these slides. In preparation for that, however, I would like for you guys to make sure you read the chapter on Chapter 8. Okay, some of the information may begin to become a little bit heavy, and I want to make sure that you have some prior knowledge about hypothesis testing, particularly, and I'll go ahead and kind of give you some of that information, some of the decision theory terminology. It'd be great if you could go ahead and familiarize yourself with some of those, and thinking about the types of errors that people make or that researchers make based on their data set. Okay, so we can make things known as type 1 and type 2 errors. So we'll review that next time. So it would be great if you could go ahead and in the textbook, read about those particular sections, again, so you have some prior knowledge coming in. I do have suggested problems for Chapter 8. You may begin some of the first ones in this data set. You can see I'm suggesting 8.1 through 8.13. Begin to work some of the initial ones that we've already discussed and based on what we've discussed today. If you're having difficulty with understanding anything I've reviewed to this point, please post that to the discussion board so that way your TA can review some of those in a live session with you, or I can get back to you just via discussion board. Also, I want to extend the opportunity to students. If you prefer to meet with me one-on-one or meet with your TA, we're willing to do so. So just because this is an online class doesn't mean that we couldn't interact with one another. So if you're interested in scheduling a meeting, just shoot me an email in Blackboard and I'll be happy to set something up for you. The meeting could involve going over any of the problems or any of the information we've gone over to this point, or if you're just wanting to discuss your status in the class, if you're feeling like you've fallen behind, please, I encourage you to contact me early on and let's talk about ways to help you guys, because I really do care about your success in this course, and I think that there are important study techniques that hopefully I've sort of talked about a little bit throughout my lectures, but I hope that you will implement into your own study habits. Statistics is not an easy course for many. Okay, so for some of you who are mathematically inclined, some of this information may come easy to you. Others may be a little freaked out by the course. Okay, so I do encourage you to come forward sooner rather than later so that way we can help you so you do not fall behind. It's very difficult to catch back up once you have fallen behind. Okay, well that brings us to a conclusion on Part 1 of Chapter 8. Next time we'll go over the remainder of these lecture slides. Thanks so much and have a great day.